Okay, let's continue. So we have been looking at the poles and zeros in our circuits. We looked at the common drain. In the last week we looked at the common source. We saw the Miller effect and how we can use Miller approximation to get the pole locations easily. So common source done, common drain done. Common gate is a practice problem. That's not difficult. So single stages are done. So now let's start to look at our differential amplifier. So let's look at our 5 transistor OTA. Let me sketch the schematic once. So I have the PMOS current mirror here. And the NMOS drifter. And I am biasing it with the current source like this. Right. So these are the inputs and this is the output. So first let's start to look at the poles in this circuit. And as you guys already know, the poles, location of the poles does not depend on the input. So for pole calculations, I can assume that the inputs are 0. So basically that means that for small signals V1 and V2 are grounded. Right, I don't worry about this. Again, for small signals the supply is grounded, this bias voltage here is grounded. So first let's mark all the capacitors in the circuit. So in this circuit, besides the ground or the reference node, how many nodes are there in the circuit? 3, right? So I have 1 node, 2 and 3, right? So let's just lump all the capacitors at those nodes. So let us say at the output here I have let's say the OTA is driving a load capacitor here. So I call it CL. This will also comprise of all the parasitic capacitors from this node to ground, right? So I'll lump it all together as a single cap CL. So similarly I'll have from this node to ground I'll have a capacitance. So let me lump all those parasitics and call it as Cx. And maybe just to make sure you understand what parasitic capacitors will come here, can you tell me what all parasitic capacitors will contribute to Cx? Let's write it for 1. I mean, remember this node I have 3 transistors. So let's start from each transistor. For M0, what all parasitic capacitors will contribute to Cx? Yeah, remember from drain to gate, because gate is incrementally short, and yeah, drain to bulk is the main thing. So basically that is going to be I'll just write it, drain to bulk of 0 plus gate to drain of M0. Those are the 2 things. Similarly for M1, M2, I mean let's look at M1. For M1, what parasitic capacitors you will consider? From source I have source to gate or gate to source capacitor, as well as source to bulk, right? So I'll mark those 2. So CGS of M1 plus source to bulk of M1. Same thing will happen for M2 also. Right? Again, so I'm sure for other capacitors you can lump the same way, so I will not write in detail. So let's we'll erase it later. Similarly, at this node I have a bunch of parasitic capacitors which I lump it as a single capacitor C1. Okay. I'll erase Cx, I think that is fine. So here I'll basically ignore the gate to drain capacitance here, because I mean if I include it, it unnecessarily complicates things. And in practice it's a reasonable approximation to make, because gate to drain capacitance in practice is much smaller in magnitude compared to the gate to source capacitances. So one assumption I'll make is the following. I basically ignored CGD just to keep things simple. Great. So now how many poles are there in the circuit? How will you find the number of poles? You look at the number of independent capacitor voltages. I can initialize all 3 capacitor voltages independently without any contradiction. So 3 poles. So that is clear. And let me mark. And let's say I also make an assumption that my load capacitor is much greater than all the other parasitic capacitors Cx and C1. Yeah, it can, I mean, it can be an external load. It can be, let us say this is driving some other circuitry. The input capacitance of that circuitry can be CL. Any load that this guy sees is, I am calling it as CL. Yeah, it includes all the parasitic capacitors from this node. But typically, I mean, the parasitic capacitors here are the drained parasitics, that's much smaller. So mostly the load cap will dominate. And we are assuming that this load capacitor for this OTA is much larger than all the other internal parasitics. So if I make these assumptions, how can I approximate the pole location now? Yeah, I can assume that the low frequency pole will be contributed by which capacitor? CL. So which means I'll assume that low frequency pole is due to CL. And for that, what will I assume for other capacitors C1 and Cx? I'll assume that they are open. So which means I can now directly write my, again this is an assumption that we are making, right? So let's write it first and then see if it's fine or not. So for finding the low frequency pole, now I know that the low frequency pole can be associated to one capacitor CL. So the pole location is 1 by R times C. C is this. What is the resistance looking here? Again, remember when I am doing this, I am basically considering C1, Cx to be 0, right? There are no capacitors. So what is the resistance looking here? Yeah, we have already seen. I mean, it is, let us say, R0 of the PMOS parallel to the R0 of the NMOS. I write it in terms of conductance, so it is the sum of the two conductances. And in this calculation, we ignore the other capacitors. They are open. So now this is an assumption that we have made that the capacitor CL contributes to the low frequency pole. Let's see if it is fine. So the output resistance here, do you think it's going to be large or small? The output resistance here, it's going to be a large number, which means the conductance is going to be a small number, and the capacitance CL is already assumed to be large. So it's reasonably good that the assumption is valid. Is it okay? So now that's the low frequency pole. Now we have two more poles. I'll call it P2, P3. So now if you are looking at these high frequency poles, by high frequency I say frequencies beyond this pole frequency, the low frequency pole. So for these pole locations, what can I assume CL to be? I can assume that to be short circuit, because now CL is, we are looking at frequencies much greater than the first pole. So CL will most likely behave like a short circuit. So for these both poles, I'll assume that CL is short. Again, now we have a second order system. So when can I write the pole as 1 by R times C? When they are uncoupled, or if you have a case where one capacitor is much larger. In this case, both are parasitic capacitors, so you might not be able to make any comments easily. So let's see if they are uncoupled. And how do you check if this capacitor Cx is uncoupled from C1? Okay, we'll open our short C1 and we'll see the resistance seen by Cx. So let's do that. So first let me assume that Cx is open. So I've opened it. So I'm interested in finding the effective resistance seen by the capacitor Cx. So I see one resistance looking down, something to the left of it, and something to the right of it, right? So what is the resistance looking down? It is gate and source are shorted. We are looking into the drain. This is R naught of the transistor M0, correct? And what is the resistance looking to the right side, the one I have marked here? Remember, I am looking into the source of this transistor M2 and the drain is small signal ground. So the resistance looking there is how much? I'll say Gm of NMOS. I mean, I don't want to give numbers here. Is that okay? Similarly, what is the resistance looking here? I mean, remember, the resistance looking into the source is 1 by Gm, provided if the drain side resistance is much smaller. What is the drain side resistance here? It is 1 by Gm of which transistor? PMOS transistor. So this is basically 1 by Gm of the PMOS transistor. That is the resistance you have at the drain side. So that's going to be much smaller than R naught of your NMOS. So it's reasonably fine to approximate this to be 1 by Gm of NMOS. Again, remember, when I say the looking in resistance is 1 by Gm, it is the resistance from this node to ground. Okay, so if I were to redraw this, the bottom side I have a resistor like this, R naught 0. To the right side I have a resistor to ground, which is 1 by Gmn. To the left side I have another resistance connected to ground. It is the resistance from this node to ground, right? It is not as though you can replace this with an effective resistance of 1 by Gm. I mean, it is not like, you know, these two terminals you put a resistor like this. This is a mistake some of you made in the last quiz. I mean, remember, I can replace between these two, I can replace it with a resistor like this. Under what conditions? No, I mean, okay, maybe the question is not clear. What I'm saying is, if I have it like this, let's say the drain resistance is much smaller, the resistance looking is 1 by Gm, which means it is as though I have a resistance with a value 1 by Gm to ground, right? But when can I say that? That is, I have something here. When can I replace this with a resistance of 1 by Gm? When it becomes a single port network, that is, if you have some connection like this, then this is basically a resistance of 1 by Gm. Then if you have a resistor at the top, what is the resistance now looking here? This is now a single resistance with a value 1 by Gm. So 1 by Gm and Rx come in series. So here is where you can say it's 1 by Gm plus Rx. Correct? So whereas here, if Rx is assumed to be much smaller than, let us say, R naught, the resistance looking here is just 1 by Gm. Is that clear? So this is the equivalent resistance when C1 is open. And how can you approximate this as? Yeah, I mean, R naught is going to be much larger than 1 by Gm. So it will be these two fellows that will contribute. So you have an effective resistance of how much? 1 by 2 Gm. So I'll write it here. When C1 is 0, the resistance I see is 1 by 2 Gm. Is that okay? So let me move on. So now let me consider C1 to be short. So now C1 is shorted. Now tell me, will the looking in resistance down change? I am looking into the drain of M0, that's still R naught. What about the resistance looking to the right side here? That is also 1 by Gm. What is the resistance looking here? That is also 1 by Gm, because here also drain is shorted. So which means the resistance is same whether my C1 is open or C1 is short circuit. So the capacitors C1 and Cx are coupled or uncoupled. So that makes our life simpler. So I'll erase this. This is Cx. We'll go to next page. So I'll mark C1. So the resistance I have, resistance seen by Cx is basically 1 by 2 Gm. So the pole location is how much? What is the pole location then? 2 Gm n by This we are writing because I found that Cx and C1 are uncoupled, right? So we remark it here. Right? Cool. So now we just found that Cx is uncoupled from C1. So which means, do you think C1 will be uncoupled from Cx? I mean, obvious. So which means C1, the third pole, you can write it directly as 1 by the resistance seen by C1 times C1. But let's verify that the resistance seen by C1 doesn't change irrespective of Cx being open or short. So first let's look at the case when Cx is open. I've opened it Cx. I'm interested to find the resistance looking here. So I'll actually erase this. As usual, I'll apply a test voltage. For example, say, what will be the current drawn by this transistor here? I applied a test voltage at this node. This is connected to the gate of the transistor. So the current drawn will be, how much will be the current? Gm of the PMOS times V test. You have Gm VGS. Plus you also have the current through the R0 of the transistor, and how much will be that current? Vt by the current is Gm VGS plus the VDS by R0. So VGS here is V test. VDS is also same as V test. And again, for practical purposes, I can assume that this current due to R0 is much smaller. Now you also have something looking down. So looking down, I'm looking into the drain of this transistor. So do you think the resistance is going to be small or large? Looking into the drain of this transistor, will the resistance be large or small? It's going to be really large. So the current that will be drawn here is going to be much smaller compared to this current. So this current you can typically ignore, not a problem. But please remember, this voltage V test is also applied to the gate of the right side PMOS transistor. So which means this will also draw current GMP times V test. Now this current can either flow through the R0 of the transistor, it can flow here, it can flow down, or it can flow to the short circuit. Where will it flow to? All of the current will basically prefer going to the short circuit. So will there be any current, any portion of this current coming here? Right. So which means the total test current I have is just GMP times V test. So the resistance is how much? 1 by Gm. Right. So I'll say that R approximately 1 by GMP. But remember, if this is not a short circuit, then you have some portion of this current that can flow down, that will also contribute. This is something we saw when we looked at impedances in this circuit. So if this is not short circuit, then a portion of this current GMP times V test will basically flow down. That will also add to your test current. So the resistance was not 1 by Gm, it was 1 by Gm into a fraction. Correct? Whereas in this particular experiment where I am shorting this output side, this will not contribute. Okay, cool. And now, I mean, this is when Cx is open. So now, even if I assume that X is short circuit like this, it's going to be same. Looking up, it's going to be 1 by Gm of this transistor. So that is going to dominate. So the resistance seen by C1 is basically 1 by Gm of PMOS transistor. So let me write it. Let me erase all this. So one of the poles we saw was 2 GMN by Cx. So this is going to be GMP by C. Again, just to remark, C1 and Cx are uncoupled. This is clear? Any questions? Okay. So if the pole locations are clear, then let's move on to zeros. So let me see. So let me solve this. I will also draw the load capacitor now. So I'm interested in finding the zeros in the circuit. So if I ask you to find the zeros in the circuit, what should be the question you should ask me? Where is the input and where is the output? Very good. And let us say I tell you that these are the inputs V1, V2, and this is my output Vout. Now note that here I have how many inputs? 2 inputs. So technically I can define 2 different transfer functions from each of the inputs to the output. So with respect to V1 I can have a transfer function, say A1 of S. With respect to V2 I can have another transfer function A2 of S. Now both these transfer functions will have the same poles because poles are a natural characteristic of the system, but the location of zeros will be different in the 2 transfer functions. Okay. Now remember, we are dealing with a differential amplifier. So instead of treating the inputs individually as V1, V2, what can we do instead? We can decompose as a common mode and a differential mode part. So instead of computing the transfer function with respect to the individual inputs like this, it makes more practical sense to think of them as a differential input and a common mode input. I'll find 2 transfer functions, one corresponding to the differential mode signal, one corresponding to the common mode signal. Again, as usual, the pole locations in these 2 are going to be same as before we computed, only the zeros will change in the 2. So we are more interested in the differential mode performance. So today we look at the zeros in the differential mode transfer function. So the common mode zeros, that will be a practice problem for you to work out. I'll give it the next week. So let's now try to find the zeros in the differential mode transfer function. So I'll rewrite it. This is zeros in the differential mode. So which means the inputs I'll be feeding in will be plus VID by 2 on one side, and on the other side it's minus VID by 2. Done? Okay, so now we have this. Tell me, how will you find if you have zeros in the circuit or not? Yeah, you can short. Tell me how many capacitors you can short simultaneously here but still have non-zero output. 2. Which capacitors can you short simultaneously? I can short C1 and Cx, right? Because if I short these 2, you see that my output can still be non-zero because this is now acting like a separate common source, right? This source is grounded for M2. You are applying input at the gate, so you'll have a non-zero output. So I can have 2 zeros in this differential mode transfer function. Let me erase this. So I'll write it here. I have no. This is not an assumption, so I will mark it here. 2 zeros because I can short C1 and Cx. So how will you find the location of zeros now? We assume that Vout in the Laplace domain is 0, and then you try to solve the circuit as before. You have 3 nodes. So node 1, node 2, node 3. You write 3 KCL equations. However, only these 2 node voltages are unknown. Vout of S is known to be 0. So the third unknown will be what? The complex frequency S. So you solve for it and you will get 2 different zeros here. But as I mentioned, my life is too short for me to do algebra in class. But you guys have much longer life, so you guys work it out. I'll again give it as a practice problem. Instead of doing this, I will take a slightly shortcut, which is what is generally done. I'll make an approximation to make my life simple, and the approximation is this. Erase this. So tell me, if I am looking at a differential mode excitation, if this was a truly symmetric circuit, what could you have done to simplify the calculation? Yeah, this node potential, you can assume that for small signals it is 0. But this is an asymmetric circuit or symmetric circuit? Why is it asymmetric? Okay, let's say if I don't have this, will this be symmetric now? Yes or no? Look at the circuit, is it symmetric now? Yeah, I mean, see, remember, I have CL here and CX here, right? Sorry, CL and C1 here. So I have asymmetrically loaded the two sides. Still, it is not symmetric. Okay. So for DC, yeah, fine. For DC operating point, this is now symmetric because capacitors are open. As long as for DC signals or small signal DC calculations, it is fine. But when you are looking at poles and zeros, this is not fine. Okay. So here we have twofold problem. One is because we are making this current mirror connection. Second is because you have asymmetrical capacitive loading on the two sides. But remember, this asymmetry is happening at the drain side of the NMOS transistor. Now, we already saw before that it is the R0 of these two transistors that couple the information from the asymmetrical drain node to the source node. So, if I assume that the R0 for the NMOS transistors here is infinity, then whatever asymmetry is happening here is not coupled to this node. Correct? So which means then what can I say about this node now? So already I made two assumptions. If I make a third assumption that R0 of the NMOS transistors is infinity, then although this is asymmetrical, I can argue that my this common source node will be 0 for small signals. Okay. It's very trivial. You can just apply KCL at this node, ignoring R0. You will find that Vx will directly become 0, right? So now is when things become interesting. I know this node is small signal ground, so I can redraw the circuit this way. This is grounded, this is grounded, grounded. So which means, do you think the Cx capacitor is contributing to my circuit's transfer function? Yes or no? No. So basically this fellow is not contributing at all. Correct? Because both terminals of this capacitor is grounded. So now look at this circuit alone. This is my relevant circuit for differential mode signals. And in this circuit, tell me how many poles I can have. 2 poles, because I have only 2 capacitors now. And how many, I'll write here, I seem to have 2 poles here. And how many zeros I can have here? I can only short 1 capacitor here. So looks like I should have 2 poles and 1 zero. But 10 minutes back I convinced you that we have 3 poles, and in fact we computed the location of all 3 poles. 1 minute back I convinced you guys that I have how many zeros? 2 zeros. So looks like we should have had 3 poles and 2 zeros. But looks like in this particular case I end up with 2 poles and 1 zero. So what happened to the additional pole and 0? That's the only logical explanation, that the additional 0 and pole, they somehow fall on top of each other and cancel if R0 is infinity. And that's exactly what will happen. So in fact, in your practice set, I'll ask you to compute the location of these 2 poles, zeros. You compute the location of these 2 zeros, and then you tend R0 of the NMOS to infinity. Then you will find that one of the zeros will become equal to the pole you computed as 2 Gmn by Cx. So those two kind of cancel. So that's a special case where you ignore the R0 of the NMOS transistor here. Then you will have this. This is again an example of uncontrollable or unobservable state, where you have an exact pole 0 cancellation. But strictly speaking, the circuit has 3 poles and 2 zeros. just that in this particular condition, that one extra, that one pole and 1 0, they fall on top of each other. So at least now I know information about one of the zeros, that for R naught being really large, I know one of the zeros will tend to 2 GMN by Cx, right? That is the pole we computed here. So now at least I know approximately one of the zeros will be at this location for large values of R naught. So let's compute the other zero location by taking this simplified circuit. Okay. Whatever I've told so far, is it fine? So now I'll basically erase this because it is not relevant for us. So let's now compute the location of 0. Again, how will you find the 0 location here? Sorry? Yeah, assume that V out of S is 0 and then what do you do? I'll sit and the 0 will come directly. What should I do? Huh? Yeah, okay, we apply the KCL at this node. So what is the small signal current flowing in this direction? GM or minus GM? Yeah, so let me write it as I2. So I2 of S is minus GMN times VID of S by 2. Correct? So sum of this current and the current flowing through the PMOS transistor must be equal to 0. So let's try to find the current I4. Now remember, the current here is flowing because we have some gate voltage applied here, and this gate voltage is because we have some current getting pushed into this transistor. So all I need to find is the current flowing in the PMOS transistor here. If I know I3, I know I4 is same as I3. Again, basic current mirror action. So first tell me what is the current flowing this way through M1. Yeah, so I1 of S is minus GMN VID of S by 2. So I have a current I1 that is getting pushed into this node. This current can either flow through the transistor here or through the capacitor here. How much of the current will flow here? How will you find it? Huh? Yeah, remember I have made this gate to drain connection, so this is acting like a resistor. So I have a current division between a capacitor and a resistor. So that is going to be my I3. So tell me what is I3 in terms of I1? What is the factor? Yeah, I'm interested in finding the current through the resistor 1 by GM. Yeah, I can do this. Yeah, I can directly write it like this: conductance by GMP plus. You either write as other impedance by the sum of impedances, or you write it as the conductance, the current sees, by sum of the conductances. Both are same. You would have written this as I1 of S times 1 by SC1 by 1 by SC1 plus 1 by GM. Correct? This is an impedance which has a resistance of 1 by GM, so it's a current division, right? That's all. So now I have found both the currents, so I can apply KCL now. Same thing, I2 of S plus I4 of S must be equal to 0. So let me substitute this. I2 is minus GMN VID by 2 of S. I4 is same as I3, so let me remark it here. So this is going to be minus GMN VID of S by 2 times GMP by GMP plus SC1 equal to 0. So now you can rearrange this and you will find that the 0 will be at minus 2 GMP by C1. It's a simple, manipulation. So this will be the 0 location. So is it clear how we found the location of 0? Finding location of 0 is simple. You just assume that the V out in the Laplace domain is 0 and then apply KCL. That's it. You try to solve for the circuit, but instead of solving for the node voltage, you find the complex frequency S. That's all. Is it okay? Cool. So basically, to summarize, let me see if I can copy paste it. Awesome. Yeah, to summarize, if I, in the differential mode, if I ignore the R0 of the NMOS transistor, I'll eventually have only 2 poles and 1 0, right? And the low frequency pole is contributed by the capacitor CL, and the location of this is, we computed the conductance, output conductance by CL. For this you assume C1 to be 0. And what is the pole here? What is the pole due to C1? GM of which transistor? GM of the PMOS transistor by C1. For this we can assume CL to be short. And the 0 location we just computed, this is minus 2 GMP by C1. So this is an LHP 0. But remember, oh, okay, tell me, this is LHP and RHP. I mean negative, right? LHP. What's the confusion? I mean, okay, the reason why we don't write poles as negative is because the transfer function we assume is of this form, 1 plus S by P1. So inherently the assumption is poles in the left half of S plane. So we don't write the negative sign explicitly. Correct? Because this is the standard form of transfer function where by inherent assumption the poles are assumed to be in the left half of S plane. So you don't explicitly mention the negative here, right? Okay. And again remember, this is valid if for large values of the R0 for NMOS. Otherwise we have a third pole at this frequency 2 GMN by Cx, and you have an additional 0 close to this frequency, and when R0 is signoid, those two cancel each other. Cool. So let me take this. So any questions so far? Okay. Now couple of jargons to remember. So typically the low frequency pole is what we call as the dominant pole. Have you heard this term before, dominant pole? Yes. Okay, why is it called dominant pole? Like this low frequency, it's near origin. Okay, so why should that be dominant?
The transfer function can be approximated to this pole when there is a particular condition. Other poles are far away from.
Yeah, so why is, I mean, okay.
The transient response is controlled by that.
Can you elaborate? Can you, correct, it's right. So what do you mean by it's controlled by this?
Means the pole system speed is controlled by this flow.
Yeah, see, I mean, so if I had to put this into other words, so if I have a pole like this, right? A transfer function having a pole like this, what is the impulse response of this? E power pt, correct? Let me call it as p, it's pt. So if I have two poles, so I have two exponentials like this. Impulse response will have two exponentials. So basically, let us say one does something like this, other might do something like this. Now which of these two will correspond to a low frequency pole, yellow one or blue one? Which will decay faster, if p is larger or p is smaller? When p is larger, this will decay faster. So which means this will correspond to the low frequency pole, and as you see, the final settling is kind of dominated by the lowest frequency pole. So that's why we call this the dominant pole. The analogy I give is, let's say you go to mess with a group of your friends. There will be one guy who will eat really fast, finish in 2 minutes, and there will be one guy who will be eating ultra slow. He will be there till the end of the mess, but the entire group can leave the mess only if the slowest eating person finishes, right? So same thing here. So here the final settling or the final speed is always determined by the lower frequency pole. So we call this the dominant pole. Okay, so if I call this the dominant pole, what do you think I'll call the other pole as? I mean, English opposite, dominant. Yeah, second standard English, nothing complicated. This is non-dominant pole. And sometimes in the context of the 5 transistor OTA, this pole is also referred to as mirror pole, probably because it is coming from the current mirror we had in the PMOS. Because remember, the PMOS we have is a current mirror, and because we have the pole coming from that, it's called as mirror pole. Yeah.
If we calculate pole zeros in the circuit,
okay,
one of the pole will come exactly like this to GMP upon C1.
One of the zeros, yeah, it will come as 2 GMP by C1. Yeah, we just computed, right?
Second pole will be
second zero you are saying?
Yeah?
The second zero.
That is approximated.
Yeah, hold on. So we technically have 2 zeros here. Okay. Again, if you put R0 of the NMOS to infinity, one of the zeros will be this, other zero will be what we computed.
If R0 is not infinity, one of the zeros will be this only, no?
Yeah, it will be close to this, right? I mean, roughly this. I mean, see, the assumption is always GM is much greater than 1 by R0, correct? So technically speaking, if you want to be really accurate, the zero location will also depend slightly on R0. But the assumption is that R0 is large, that this is approximately the zero. So here if you see, the non-dominant pole is at GMP by C1, and I have a zero much closer to it, at twice the frequency. So whenever you have poles and zeros located close to each other, so we call this a pole zero doublet. So I'll just mark it here. Anytime you have a pole and zero located close to each other, we refer to the scenario as pole zero doublet. These are just terminologies to have in mind. So now if I try to sketch the Bode plot of the differential mode transfer function, this is frequency. So what is the DC gain of the 5 transistor OTA? How much is the DC gain here? GM of which transistor? Yeah, M1 M2 times the output resistance is R0 of this transistor parallel to this. So that will be, let us say, this value. This is the DC gain. I'll call it as some A0. And then you have the dominant pole. After you hit the dominant pole, what will happen to the response? Minus 20 dB per decade. And then let's say you get the non-dominant pole here. So here it will become how much? Minus 40 dB per decade. But immediately after the second pole, what do I have? The zero. The moment I encounter the zero, what will happen to the slope again? Minus. So which means for practical purposes, I can approximate this as a first order system like this. Because although I have these two additional things, if I squint my eyes and see, it will look like a straight line. So we can approximate the transfer function as a first order transfer function, which is A0 by 1 plus S by P1. P1 is the dominant pole. And typically, if you have a large load capacitor in your OTA, the dominant pole can be associated to that load capacitor and the output resistance. This is assuming CL is basically, really large. Okay.